Take the planet you are standing on right now and squeeze it. Keep squeezing until Earth, all of it, the oceans and the mountains and the iron core, is compressed into something the size of a peanut. That is roughly how much crushing it takes to turn a planet into a black hole. Hold that image for a moment, because you are about to need a much stranger one. Now take the entire visible universe. 2 trillion galaxies. Every star inside every one of them. Every planet, every comet, every speck of drifting dust, every quiet corner of empty space between them. Compress all of it, the whole of everything that exists, down to a single point smaller than a proton. That point is where you came from. 13.8 billion years ago, it was the entire universe, folded into a space too small to see, and for a sliver of a second, it was the only thing that existed. What if you could stand there, not read about it in a book, not watch a simulation of it on a screen? What if you could actually travel backward through time, past every star that has ever burned and every galaxy that has ever spun, until you arrived at the instant before there was a universe at all to arrive in? And what if, once you reached it, you did not stop? What if you kept traveling, past the singularity itself, past the beginning of everything, into the strange and mostly unanswered territory that lies before the Big Bang, a place where, by definition, there was no space to stand in and no time for the standing to happen in, a place that may not be a place at all. Tonight, we take that journey twice. First backward, through 13.8 billion years of unraveling galaxies, dimming stars, and cooling light, until we reach the instant the universe began. Then further, past that instant, into the handful of serious ideas that scientists have proposed for what, if anything, existed before it. We will not pretend to answer that second question with certainty. Nobody can, not yet, but we can walk through what is known, what is guessed at, and where the line between them sits. The Big Bang is one of the strangest and most misunderstood events in the story of everything. Most people picture it as an explosion, a burst of matter and light hurling outward into a waiting, empty darkness. That picture is wrong, and correcting it is where our journey begins. The Big Bang was not an explosion into space. It was the beginning of space itself. Before it, by the best evidence available, there was no here for the beginning to happen in, and no earlier for it to have been preceded by. Time itself is thought to have started at that same instant. To understand what it would actually mean to stand inside that moment, we first need to understand how anyone knows it happened at all. Nobody was there with an instrument to measure it. No telescope existed to watch it unfold. And yet scientists speak about the first fraction of a second of the universe's existence with a surprising amount of confidence. That confidence comes from evidence still visible today, written into the light of distant galaxies and the faint static that fills empty space. Once we understand that evidence, the journey backward will make more sense, because we will know exactly what we are traveling toward and how we can be so sure it is there. From this moment, on Earth, in the present day, we begin moving backward, not gently, not in gradual steps of centuries or millennia, but in leaps of hundreds of millions of years at a time, watching the universe run in reverse until the vast, star-filled sky above you collapses into something almost too small and too hot to imagine. That is the first half of tonight's journey. The second half begins where the first one ends, at the edge of everything we can know, looking for what might lie beyond it. Along the way, the ordinary rules of experience stop applying. Distance stops meaning what it usually means. Heat climbs past any number that has a name attached to a familiar object. Sound exists without air to carry it. Light exists in colors no human eye has ever registered. None of this is exaggeration for effect. It is simply what the physics describes, as closely as physics is able to describe a place this far outside the boundaries of ordinary experience. We will move through it slowly, one stage at a time, translating each stage into something closer to scale, closer to a feeling, than to a raw number on a page. There is no need to remember every figure. What matters is the shape of the journey, the way one condition leads into the next, the way a universe this violent and this strange eventually settles into the quiet, starlit sky you already know. Somewhere in that unfolding is the answer to a simple question. Were you there, in some form, at the very beginning? And somewhere past it is a second, quieter question about what might have existed before the beginning began. Here is how we know the universe had a beginning at all. Scientists studying distant galaxies noticed something strange in their light. As those galaxies moved away, their light stretched toward longer wavelengths, shifting toward the red end of the visible spectrum. This is called redshift, and it works on the same principle as an ambulance siren changing pitch as it passes you on the street. When a sound source moves toward you, the waves it emits bunch together, and the pitch rises. When it moves away, the waves stretch apart, and the pitch drops. Light behaves the same way. A galaxy moving away from us stretches its own light toward red, and the faster it moves, the more pronounced that stretch becomes. When astronomers measured this effect across thousands of galaxies, they found the same pattern everywhere they looked. Nearly all of them are moving away from us, and the farther away a galaxy sits, the faster it appears to be receding. That observation only makes sense if space itself is expanding, carrying galaxies apart the way raisins in a rising loaf of bread drift apart from each other, not because the raisins are moving through the bread, but because the bread between them is growing. If the universe is expanding now, then logically, it must have been smaller in the past. Run that expansion backward far enough, and everything, all the matter and energy that exists, converges on a single point. That point, impossibly hot and impossibly dense, is what scientists mean by the Big Bang. It happened 13.8 billion years ago, and the light from that era, cooled now to a faint microwave hum, still surrounds us in every direction, a fossil signal from the universe's own infancy. One detail worth settling before the journey begins. The Big Bang did not happen at a specific location that we could point to and travel toward. It happened everywhere. Space itself did not yet exist as separate points that a singularity could occupy. The singularity was not a small object sitting inside a larger, empty space. It was space, compressed to the smallest scale physics has a name for. That means traveling to it is not a matter of traveling somewhere. It is a matter of traveling to some when. So we will not go looking for a location. We will go looking for a time, beginning now. In the present, we travel backward, watching the sky above you shrink, brighten, and eventually vanish into something no sky has ever looked like before or since. Every measurement guiding that journey, every figure and comparison offered along the way, rests on evidence gathered here, on Earth, by instruments pointed outward at a universe that has been patiently leaving clues about its own origin for as long as there has been light to carry them. You begin on Earth, tonight, in the ordinary dark of a world that has existed for 4.5 billion years. Above you, the stars sit where they always sit, fixed points scattered across a sky that looks, for all purposes, permanent. That permanence is an illusion built from the shortness of a single human life. Every one of those stars is moving. Every galaxy is drifting apart from every other galaxy, and the whole arrangement above you is a single frame taken from a very long film. Tonight, that film runs backward. On an ordinary night, a few thousand stars are visible to the naked eye, a small, deceptive sample of the roughly 200 billion stars filling the Milky Way alone, itself just one among an estimated 2 trillion galaxies scattered across the observable universe. None of that vastness is apparent from the ground on any given evening. It takes a deliberate act of imagination, or in this case, a deliberate act of time travel, to feel the true scale of what surrounds a single planet on a single, ordinary night. The first thing you would notice, if you began traveling back through time from this point, is not that space gets younger, it gets smaller. Two galaxies that sit millions of light years apart today would draw closer together the further back you traveled, the space between them contracting the same way it once expanded, only now in reverse. This is not a metaphor. It is the same expansion observed by astronomers, simply run the other direction. A century back, the difference would be too small to notice with the naked eye. 100,000 years back, still too small. But push past a few 100 million years, and the sky above you would begin to visibly change. Galaxies that once sat comfortably apart would begin to crowd the sky, their light brighter, their edges sharper, because you and they would no longer be separated by such enormous distance. Somewhere in this stretch of the journey, roughly 4.5 billion years back, the ground beneath your feet would stop existing. Earth itself formed out of a swirling disk of gas and dust orbiting a young sun, and traveling further back than that means traveling to a time before there was an Earth to stand on at all. From this point in the journey onward, you are not walking through space so much as drifting through it, an observer with no planet beneath you, watching a universe that has not yet built the one place you have ever called home. The sun would vanish not long after Earth does, in reverse time. It formed 9.3 billion years after the Big Bang, out of a collapsing cloud of gas and dust seeded by the deaths of earlier generations of stars. Traveling backward past that point means watching your own star disperse, its light fading, its mass scattering back outward into the cloud it once condensed from. The warmth that has defined every day of human history simply is not there yet. There is only the colder light of older, more distant stars, and even those grow scarcer the further you travel. Stars do not simply sit quietly in this reverse timeline either. Some of them end their lives in supernovae, explosions bright enough to briefly outshine an entire galaxy, scattering the elements they spent millions of years forging in their cores. Run that process backward, and a supernova does something that looks almost impossible. It draws its own wreckage back inward, gathering scattered gas and dust and light back into the shape of a single, swollen star. You would watch this happen again and again across the reverse sky, a slow, silent unraveling of stellar death into stellar life. Galaxies themselves would begin to change shape. A spiral galaxy, its arms trailing gracefully outward the way water trails from a spinning sprinkler, would slowly unspin. The distinct, curling structure that took hundreds of millions of years to form would loosen, then blur, then disperse, stars scattering back into a looser and less organized swarm. Clusters that took shape over cosmic ages would dissolve back into the diffuse clouds of gas and dust they were assembled from. Nothing about this process would look destructive. It would simply look like construction running the wrong way, each structure quietly disassembling itself into its raw material. There is a sense in which telescopes have already performed a version of this journey, without anyone needing to travel anywhere at all. Light takes time to cross distance, and the farther away an object sits, the older its light is by the time it reaches an observer. Looking at a galaxy several billion light years away is not looking at that galaxy as it exists now. It is looking at light that left it billions of years ago, a direct window into the past, delivered without any need for time travel beyond the ordinary patience of waiting for photons to arrive. In recent decades, astronomers have built telescopes sensitive enough to gather extraordinarily faint, extraordinarily old light, capturing images of galaxies as they appeared within the first few 100 million years after the Big Bang. Every one of those images is, in its own way, a photograph of an earlier stop along the very road you are now traveling in reverse, evidence gathered from Earth that confirms the same reversed unraveling described here, layer by layer, without a single instrument ever leaving the ground. The Milky Way itself, the galaxy that has always been home, would not be exempt from this unraveling. It formed gradually, over billions of years, through the merging of smaller galaxies and the slow accumulation of gas drawn in by gravity. Traveling backward through its history means watching those mergers reverse, the galaxy shrinking and simplifying, losing the satellite galaxies it once absorbed, its spiral structure loosening into something closer to a shapeless cloud of stars and gas. Even the black hole at its center, a colossal object with a mass millions of times greater than the Sun, would shrink as you traveled back, having consumed less material the further back in time you went. Clusters of galaxies, the loose associations that group hundreds or thousands of galaxies together under mutual gravity, would show the same pattern in reverse. These structures took billions of years to assemble, gravity slowly drawing galaxies together across immense distances. Run the clock backward, and the clusters loosen, then scatter, individual galaxies drifting apart from the group they were once bound to, until the very concept of a cluster stops applying, and there is only a more even, more uniform spread of matter across the contracting universe. At the largest scales, galaxies and clusters of galaxies today are arranged into a vast, thread-like structure astronomers call the cosmic web. Long filaments of matter separated by enormous, nearly empty voids, resembling something closer to a sponge or a tangle of soap bubbles than a uniform scattering of points. That structure did not exist in the earliest universe. It emerged gradually as gravity amplified the same tiny density variations that would later leave their imprint on the cosmic microwave background, pulling matter along the densest filaments, while emptying out the surrounding voids almost completely. Traveling backward means watching that web slowly dissolve, the sharp threads and empty gaps blurring back into a smoother, more evenly distributed haze of gas, the architecture of the modern universe unbuilding itself one filament at a time. Black holes present their own strange behavior in reverse. In forward time, a black hole is defined by what falls in and never comes back out. In reverse, that same black hole would appear to eject matter and energy outward, spraying back out everything it once consumed, before shrinking and finally disappearing entirely, as if the collapse that created it had simply been uncollapsed. It is one of the more disorienting sights on this journey, watching an object defined by permanence unmake itself completely. As you continue backward, the space between everything keeps contracting. The universe you are traveling through would begin to feel less like open space and more like a crowded room, the distance between galaxies shrinking until light from one reaches another almost instantly. Astronomers estimate this contraction using the same redshift measurements that revealed the expansion in the first place, simply read in reverse. The closer you get to the beginning, the more compressed every measurement becomes. This same principle sets a hard boundary on how much of the universe can ever be seen from Earth in either direction of time. Because light travels at a fixed speed, and the universe has only existed for a finite span, there is a maximum distance beyond which no light has yet had time to reach any observer here, regardless of how sensitive the instrument used to look. Astronomers call this boundary the particle horizon, and it marks the edge of what is called the observable universe, a region roughly 93 billion light-years across, accounting for the additional expansion that has occurred while that ancient light was in transit. Beyond that horizon, the universe almost certainly continues, likely for a great deal further, quite possibly without any edge at all. It is simply that no signal from beyond that boundary has had time to arrive yet, and by the time it does, if it ever does, the universe will look considerably different than it does tonight. Dust plays its own part in this reversal. Today, interstellar space is threaded with fine clouds of dust and gas, the leftover material from dying stars and the raw ingredient for new ones. Traveling backward, that dust would not thin out. It would thicken, drawing together into the dense clouds and clumps that once seated the stars now unraveling around you. The farther back you traveled, the harder it would become to see clearly through the accumulating haze, until the sky above you stopped resembling anything you would recognize as a night sky at all. It is worth pausing here to notice how closely this reverse journey matches the evidence that first suggested a beginning existed at all. The redshift that astronomers measured in distant galaxies, that gentle stretching of light toward red as those galaxies recede, is simply the forward version of what you are now experiencing directly. Where an astronomer on Earth sees a slight reddening in the light of a faraway galaxy and infers that space between here and there is expanding, you are living that expansion in reverse, watching the space between everything visibly contract instead of merely calculating that it must be. The math that fills a textbook is, from where you now stand, simply the view outside the window. Eventually, the material filling this reversing universe would grow too dense and too energetic for ordinary matter to survive in its familiar form. Somewhere in this stretch of deep time, hydrogen, the simplest and most abundant element in the universe, the same element that fuels every star you have ever looked up at, would stop being able to exist as atoms at all. The pressure and heat climbing around you would strip electrons away from their nuclei, breaking apart the very building blocks that make up planets, stars, and eventually, much later, the body reading these words. There is a particular quality to watching a sky shrink that is hard to prepare for. On a clear night on Earth, the universe feels enormous, distant lights scattered across a dome so large it seems to have no edge. As you travel backward, that sense of scale collapses. The dome draws inward. Galaxies that once required a powerful telescope to resolve as anything more than a faint smudge would begin to fill the sky the way clouds fill it on an overcast afternoon, close, bright, and undeniably present. The sensation is less like watching a scene from a distance, and more like standing in a room that is slowly, steadily closing in around you, its walls made of light instead of stone. Time itself would begin to behave strangely too. Or rather, your relationship to it would. In the earliest stretch of the journey, a single step backward might cover 1,000,000 years, the sky barely shifting from one moment to the next. But the deeper into the reversal you travel, the faster those same steps would need to move to keep pace with a universe that is compressing at an accelerating rate. Near the very end of this leg of the journey, hundreds of millions of years would pass in what feels, to you, like a single breath. The universe is not slowing down as it approaches its own beginning. If anything, every process within it is speeding up, compressed into an ever-shrinking span of time, the same way its matter is compressed into an ever-shrinking span of space. This is the point where the journey stops resembling anything like ordinary travel and starts resembling something closer to descent. Not downward, exactly, but inward, toward a condition of the universe so compressed and so energetic that words like hot and dense begin to lose their usual meaning. The temperature climbing around you would no longer be measured in numbers that correspond to anything on Earth. It would be measured in numbers that correspond only to the interior of dying stars, and then, further still, to numbers that correspond to nothing familiar at all. It helps to hold on to a comparison here, even a rough one. Earlier, we mentioned that squeezing all of Earth down to the size of a peanut is roughly what it takes to turn a planet into a black hole. The conditions building around you now are stranger than that by an almost unfathomable margin. You are not approaching the density of a collapsed planet. You are approaching the density of the entire visible universe, folded down toward a single point. Every galaxy you have ever seen a photograph of, every star that has ever been named, every planet that has ever been discovered, are all somewhere in the crush building around you, compressed together into a space that keeps shrinking the further back you travel. The experience, if you could survive it, would be one of mounting pressure and mounting heat. A claustrophobia that has nothing to do with tight walls and everything to do with the sheer density of the space itself. Space would not feel spacious anymore. It would feel like the inside of something being crushed, because that is precisely what it is. And you are traveling directly toward the center of that crush, back through hundreds of millions of years that are, from this point forward, collapsing into something closer to seconds. By the time you reach the final stretch of this reverse journey, you would no longer be moving through a recognizable version of the cosmos at all. The stars would be gone, unraveled back into the gas clouds that built them. The galaxies would be gone, dissolved back into diffuse swarms of matter, with no organized shape. Even the atoms that make up ordinary matter would be losing their integrity, unable to hold their own structure together against the climbing pressure. What remains is not a smaller version of the universe you left behind. It is something closer to the raw material the universe was built from, still coming apart at the seams as you travel further back into it. There is no gentle way to describe the transition that follows. Every landmark that has defined this journey so far, the stars, the galaxies, the dust, the very atoms making up the plasma around you, exists here only as a memory of what it will eventually become hundreds of millions and eventually billions of years in the future relative to where you now stand. What lies ahead is not a smaller, quieter version of the universe. It is the universe stripped down to a condition with almost no precedent in ordinary physical experience, a condition that requires an entirely different vocabulary to describe honestly. This is the edge of what could reasonably be called familiar physics. From here, the path forward, or rather backward, leads directly into conditions that existed only in the first fractions of a second after the universe began. Extreme heat, extreme density, and a form of matter that no laboratory on Earth has ever fully replicated. What lies just ahead is the singularity itself, and the strange, still debated question of where, if anywhere, an observer could be said to be standing while looking at it. By now, the sky above you no longer resembles a sky at all. There are no distinguishable stars, no separate galaxies, only a dense and increasingly uniform field of matter and energy packed together at a scale that keeps shrinking the closer you travel to the beginning. This is a good place to ask a question that seems, at first, like it should have an easy answer. Where exactly are you traveling to? The instinctive answer is that the Big Bang happened at a single point in space, and that traveling to it means traveling to that point, the way you might travel to a specific city marked on a map. That instinct is wrong, and the reason it is wrong says something important about the nature of the event you are approaching. The Big Bang did not happen at a location within space. It was the beginning of space itself. Before that first instant, there was no here for the singularity to occupy, because there was no here at all, not in the sense that word usually carries. This is easier to grasp with a comparison. Imagine the surface of a balloon, with dots marked across it to represent galaxies. As the balloon inflates, every dot moves away from every other dot, and no single dot can claim to be the center of the expansion. Ask any dot where the center is, and the honest answer is that there isn't one on the surface itself. The same is true of the universe, only in 3 dimensions rather than 2, and without a balloon to serve as an outside frame of reference. Every point in the universe is, in a sense, equally a center. Every galaxy could reasonably claim that everything else is moving away from it. And because every point can make that claim equally, none of them are uniquely correct, which means, in the way that matters for a journey like this one, that there is no correct answer at all. This is also why a question like, which direction is the singularity, fails to make sense, no matter how naturally it seems to follow from everything said so far. Direction is a concept that depends on space already existing, on there being a here and a there separated by some measurable distance. The singularity was not located in some particular direction from where you now stand. It was, at that moment, everywhere you could possibly stand, including the ground beneath your own feet. What this means practically is that you are not traveling to a place. You are traveling to a time. The singularity you are approaching is not a small object sitting inside a larger, mostly empty universe, waiting to be found. It is, for that first instant, the entirety of space, compressed down to a size that current physics struggles to even describe with confidence. Reaching it is not a matter of covering distance. It is a matter of reaching backward far enough that the distinction between here and everywhere else stops meaning anything. The scale involved is difficult to hold in the mind, so it helps to build it up slowly. A single proton, one of the particles that makes up the nucleus of every atom, measures about 1.7 femtometers across. A femtometer is a millionth of a billionth of a meter. To put that in a comparison, that means something. If the width of a single strand of human hair were scaled up to represent the entire planet Earth, a proton, at that same scale, would be smaller than a grain of sand on a beach. The human eye cannot see anything close to that small. Protons are not just invisible to unaided vision. They are invisible in a way that makes the word invisible feel almost too generous, too suggestive of something merely hidden rather than something categorically beyond the reach of sight. The singularity, in its earliest and smallest state, was roughly this size. Not the size of a city, not the size of a mountain, not even the size of a single grain of sand, but smaller than the particle that sits at the heart of every atom in your body. And into that space was compressed everything. Every galaxy, every star, every planet, every scrap of matter and burst of energy that would eventually spread out across 13.8 billion years of cosmic history. It is one of the more difficult facts in this entire journey to hold steady in the mind, not because the number is hard to write down, but because nothing in ordinary experience offers a comparison that makes it feel real rather than abstract. It helps to build that scale in layers, since a single jump from human-sized objects down to a proton tends to blur together into an abstraction rather than a felt sense of size. A typical atom measures roughly 100,000 times wider than the nucleus sitting at its center, meaning that if the nucleus of an atom were scaled up to the size of a marble, the outer edge of that same atom, mostly empty space threaded by orbiting electrons, would sit roughly 2 miles away. The proton itself is smaller still than the nucleus containing it in heavier elements, and the singularity, in its earliest state, compressed the entire mass and energy of everything that exists down to a scale comparable to that single proton, not to the more roomy expanse of the atom surrounding it. Every layer of this comparison, from atom to nucleus to proton, represents a further collapse into stillness and density that ordinary human scale has no real reference point for. Alongside that impossible smallness sits an equally impossible heat. The core of the sun, the hottest place most people will ever have any direct relationship with, sits at around 15 million degrees Celsius. That number alone is difficult to picture, since nothing on Earth's surface approaches even a small fraction of it. The singularity, in its earliest state, is estimated to have reached temperatures around 10 to the power of 32 Kelvin, a 1 followed by 32 zeros. Comparing the heat of the sun to the heat of the earliest universe is less like comparing a candle to a bonfire, and more like comparing a candle to the combined light of every star in every galaxy, all at once. At temperatures this extreme, individual particles as we understand them cannot hold together at all. The very idea of a proton, a neutron, an atom, breaks down entirely, dissolved into something more fundamental and far less familiar. If you were somehow present at this stage of the journey in ordinary human form, the environment surrounding you would not simply be uncomfortable. It would be lethal several times over, in ways that stack on top of each other so quickly that no single cause of harm could be meaningfully separated from the rest. The heat alone would be enough to end the story before it began. But heat is only one part of the crush closing in around you. Pressure builds alongside temperature, and near the singularity, that pressure would not act on your skin the way pressure normally does. It would act directly on your atoms, on the bonds holding together the very particles that make up your body. Under ordinary conditions, those bonds are strong enough to hold a body together through a lifetime of ordinary bumps and falls. Near the singularity, the pressure would be great enough to overwhelm even those forces, breaking matter down past the level of atoms, past the level of protons and neutrons, into a hot, dense soup of more fundamental particles, the kind of plasma that filled the entire universe in its first fraction of a second. None of this is meant to suggest the journey ends here in failure. It is meant to establish, honestly, what the environment actually is, so that everything that follows can be understood clearly. For the sake of this journey, we allow you to keep your human shape and keep your ability to observe, a small suspension of the ordinary rules of physics, granted for the purpose of witnessing something no human eye has ever actually seen. Even so, it is worth remembering, as we continue, that what surrounds you here is not survivable by anything currently known to exist, and that everything described from this point forward is being translated, as carefully as possible, into terms a human mind and a human sense of scale can hold on to. Physicists have a name for the earliest sliver of time this journey is now approaching. They call it the Planck epoch, the intervals stretching from the very beginning up to about 10 to the power of minus 43 seconds afterward. That number is almost impossible to hold in the mind in any meaningful way. It is a decimal point followed by 42 zeros, and then a 1, a span of time so short that comparing it to a single second is roughly like comparing a single second to a span many times longer than the current age of the universe. Inside the Planck epoch, the known laws of physics stop giving reliable answers. Gravity, which usually behaves as a smooth, predictable force bending space around massive objects, is thought to become as chaotic and quantum in nature as the other forces that govern subatomic particles. No experiment on Earth has ever reached energies anywhere close to what would be needed to test this directly, and no complete theory yet exists that successfully merges gravity with quantum mechanics in the way this era would require. Scientists refer to this gap honestly as an open problem rather than a settled one. The record, in the most literal sense, is incomplete, not because nobody has looked, but because the tools required to look clearly have not yet been built and may not exist for a very long time, if ever. This honesty matters here, standing this close to the edge of what can be known with confidence. Everything described about the singularity's temperature, its density, its almost incomprehensible smallness, rests on extrapolating known physics backward as far as it reliably extends, and then stopping at the boundary where that physics admits it no longer has firm footing. Beyond that boundary lies the Planck epoch, and beyond the Planck epoch lies the question this entire journey is ultimately organized around. What, if anything, came before it? That question will wait a little longer. For now, there is still ground to cover on this side of the boundary, in the era where physics still speaks with reasonable confidence. One puzzle from this era is worth mentioning here, because it explains why physicists believe something like the rapid inflation described earlier in this journey needed to happen at all. Regions of the cosmic microwave background on opposite sides of the sky, far enough apart that light traveling at its ordinary speed would never have had time to pass between them since the beginning of the universe, nonetheless show almost exactly the same temperature. Under ordinary physics, with no period of extremely rapid early expansion, those regions should never have had the chance to interact and settle into a shared, uniform temperature the way two objects placed side by side eventually do. This puzzle, known as the horizon problem, was one of the central reasons physicists proposed that the universe underwent a brief period of expansion far faster than the speed of light in its earliest fraction of a second, stretching a small, already uniform patch of the early universe out to a size large enough to account for the uniformity observed today. It is a clean solution to a real problem, though. Like much else in this stretch of the journey, it remains a well-supported model rather than a directly observed fact. It is worth being honest about another paradox built into this journey, one that has nothing to do with heat or pressure. Even setting aside the question of survival, there is a deeper problem with the idea of an observer standing near the singularity at all. To observe something usually means existing alongside it, sharing the same space, the same moment, watching from a vantage point outside the thing being watched. But near the singularity, there may not be a meaningful outside. If space itself had not yet come into being in any extended sense, then there is no proper vantage point from which a separate observer could stand and look on. You would not be watching the singularity from a comfortable distance, the way you might watch a bonfire from across a field. You would, in the most literal sense available, be asked to exist inside the very thing that had not yet finished becoming space for you to exist within. This journey does not attempt to resolve that paradox, because nobody currently can. What it does instead, for the sake of experiencing this moment at all, is grant you a kind of narrative exception, a human shape, a working set of senses, and just enough insulation from the impossible conditions around you to witness what is otherwise unwitnessable. That exception is not physics. It is a storytelling choice, made openly and without pretending otherwise, so that the physics itself, the heat, the density, the collapse of ordinary space and time can be described as faithfully as current understanding allows. It is worth noting how far this leaves current experimental science from directly testing the conditions surrounding the singularity. The most powerful particle accelerator ever built, a ring measuring 17 miles in circumference buried beneath the border of France and Switzerland, can collide particles at energies roughly equivalent to conditions that existed a tiny fraction of a second after the Big Bang, an achievement that took decades of engineering to make possible, and one that has confirmed a great deal about the physics governing that era. Even so, the energies reached by that accelerator remain many orders of magnitude short of the energies present at the singularity itself, or anywhere close to the Planck epoch that immediately followed it. Closing that gap would require an accelerator vastly larger and vastly more powerful than anything currently conceivable with existing technology, which is part of why the earliest instant remains a matter of careful extrapolation rather than direct experimental confirmation. There is one more strange feature of standing this close to the beginning, and it concerns not space, but time. As you approach the earliest instant of the universe, the ordinary flow of time itself begins to lose its footing. Time, in the way it is normally experienced, as a steady unspooling of one moment after another, is thought to have begun at the same instant space did. That means standing at the very edge of the singularity is not simply standing at an early point in time. It is standing at the edge of time's own existence, a position with no real precedent and, depending on which physicist you ask, possibly no coherent meaning at all. You are not early in the story. You are approaching the first page, the one before which there may not have been any pages. What lies directly ahead is the moment physicists call the Big Bang itself. The instant when this impossibly small, impossibly hot point stopped being a static, waiting thing and began, all at once, to become everything else. There is a temptation, standing at this threshold, to imagine some kind of countdown, a tension building toward release, the way a held breath builds toward an exhale. That framing does not quite fit what the physics describes. There is no waiting singularity, patiently anticipating its own expansion. There is simply a boundary, the edge of reliable knowledge, and beyond that boundary, a transition so rapid and so complete that it barely qualifies as a process at all. What comes next is not something that unfolds. It is something that has, in the most meaningful sense, already happened, compressed into a span of time too brief for the word next to carry its usual meaning. There is no slow approach to this next part. Everything about the moment ahead resists the kind of gradual build-up that has carried you through the journey so far. One instant, there is only the singularity, small and impossibly dense. The next instant, there is a universe rapidly becoming everything that would ever exist. Between those two states lies a span of time so brief that the word instant barely does it justice. Physicists describe this earliest period of expansion, often called inflation, as lasting somewhere on the order of 10 to the power of -33 seconds. A useful comparison, though still an imperfect one, involves the human eye blink, typically lasting somewhere between 100 and 400 milliseconds, fast enough that people commonly use the phrase, "in the blink of an eye," to describe anything sudden. The interval this journey is now passing through is shorter than a single blink by a margin so large that there are more of these tiny fractions contained within one ordinary second than there have been seconds in the entire 13.8 billion year history of the universe since. There is, in the most practical sense, no waiting around for this to happen. It simply happens, all at once, complete before there was any meaningful interval in which to watch it unfold step by step. Even so, something can be said about what filled that instant, translated as carefully as current physics allows. In the earliest fraction of a second, the enormous energy driving this rapid expansion began converting into matter and light, filling the newly stretching universe with an unimaginably hot, dense plasma. By one full second after the beginning, that plasma had settled into something scientists can describe with more confidence: an evenly hot soup of particles and energy, sitting at a temperature around 10 billion degrees Celsius. Hot enough that the words describing it stop functioning as ordinary adjectives and start functioning more like measurements on a scale with no familiar reference point. For comparison, the core of the Sun, hot enough to sustain nuclear fusion for billions of years, sits at around 15 million degrees, a figure that already exceeds anything encountered in ordinary experience by a wide margin. The universe, 1 second into its own existence, was still hundreds of times hotter than that. This early plasma was not perfectly smooth. Tiny variations rippled through it, regions where matter and energy were packed together just slightly more densely than their surroundings. In some of the tightest of those pockets, gravity acted immediately and decisively, crushing the concentrated energy into what scientists call primordial black holes. These were not the black holes familiar from later cosmic history, the collapsed remnants of dying stars. Stars themselves would not exist for roughly another 100 to 200 million years. These earliest black holes were born directly from the raw pressure of the newborn universe itself, ancient in a way nothing else in the cosmos can claim to be. Some may have been no larger than an atom, while carrying the mass of a mountain, a density that strains ordinary comparison past its breaking point. Many are thought to have evaporated over the billions of years since, releasing their mass and energy back outward in a slow process theorized, but never directly observed. Some scientists suspect a portion may still exist today, hidden among the unseen mass astronomers refer to as dark matter, a possibility still very much unresolved. Even before quarks and gluons took their more familiar forms, the universe passed through a stage in which the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, are thought to have existed as a single unified force, rather than the four distinct forces recognized today. As the universe expanded and cooled in these first fractions of a second, that unified force is theorized to have split apart in stages, first releasing gravity as a separate force, then later splitting the strong nuclear force from the combined electroweak force, and finally separating electromagnetism from the weak nuclear force. Each of these splits is thought to have released tremendous energy into the surrounding plasma, contributing to the same violent, roiling conditions filling the space around you. This part of the story remains one of the more theoretical stretches of early cosmology, resting on extrapolations from particle physics rather than direct observation, and most researchers describe it with appropriate caution as a strong working model rather than settled fact. Each of these separations left a mark on the particles that would go on to populate the rest of the universe's history. The weak nuclear force, for instance, governs the kind of radioactive decay responsible for the heat still rising from Earth's core today. A faint, distant echo of a separation that occurred within the first trillionth of a second after the beginning. It is a strange kind of continuity, watching a force take on its final, distinct identity in this furnace of a moment, knowing that the same force will still be quietly at work, billions of years later, inside a planet that does not yet exist, and beneath the feet of a species that will not exist for billions of years after that. Before any of that plasma could settle into anything resembling familiar particles, the universe passed through a stage that had no protons or neutrons at all, only their more fundamental building blocks, quarks and gluons, moving freely through an unbelievably hot soup that physicists call the quark-gluon plasma. This state lasted only a handful of microseconds, but within that brief window, the universe was too hot for quarks to bind into the larger particles that would eventually make up every atom of every object that has ever existed. As the plasma cooled, quarks began locking together in groups of 3, forming the protons and neutrons that would, much later, become the nuclei at the center of atoms. This transition, from a formless soup of quarks to bound, structured particles, marks one of the first true moments of organization in the universe's history, a small, early hint of the vastly more complex structures that would eventually follow. From there, the story moves quickly toward one of the more well-tested predictions in all of cosmology, the formation of the universe's first atomic nuclei. Beginning roughly 3 minutes after the initial expansion, and continuing for about 17 minutes after that, conditions were exactly right for protons and neutrons to begin fusing together into simple nuclei, primarily hydrogen and helium, along with faint traces of lithium. This process, called Big Bang nucleosynthesis, produced the raw material that would eventually go on to build every star, every planet, and every living thing that has ever existed, long before any of those things had the conditions needed to form. The proportions produced during this window, roughly 75% hydrogen and 25% helium by mass, match remarkably closely with what astronomers still measure in the oldest, least altered regions of the universe today. One of the strongest pieces of evidence supporting the broader picture of the Big Bang as a whole. Even earlier than this, within the first second, an almost unimaginably vast number of ghostly particles called neutrinos stopped interacting regularly with the rest of the plasma and began traveling freely through the universe, essentially undisturbed ever since. Neutrinos interact so weakly with ordinary matter that trillions of them pass through a human body every second without a single collision. This early population, sometimes called the cosmic neutrino background, is thought to still fill every corner of the universe today, a companion signal to the more famous light-based cosmic microwave background, only far harder to detect, since neutrinos slip through nearly all forms of matter designed to catch them. No instrument has yet directly measured this ancient neutrino sea, though its existence is considered a firm prediction of the same physics confirmed in every other respect, an invisible twin to the fog of light still waiting. 380,000 years further along this journey, to finally break free and travel in a straight line. Buried within this same early plasma lies one of the more persistent, unsolved puzzles in all of physics. According to the equations governing particle physics, the intense energy of the earliest universe should have produced matter and antimatter, its mirror image counterpart, in exactly equal amounts. Matter and antimatter annihilate each other on contact, converting back into pure energy, and if the two had truly been created in perfectly equal quantities, they should have gone on to annihilate each other almost completely, leaving behind a universe of light with no matter at all, no stars, no galaxies, no planets, and no observer standing here to notice the absence. Something clearly tipped that balance. For every roughly 1 billion antimatter particles created in the earliest universe, there appear to have been 1,000,000,001 matter particles, a tiny, stubborn imbalance that, after nearly all the matter and antimatter had annihilated each other, left behind just enough surviving matter to build everything that exists today. Physicists have proposed several mechanisms that might explain this asymmetry, involving subtle differences in how certain particles decay, but no complete, confirmed explanation currently exists. It remains, quite literally, the reason there is a universe left to describe it all, and it remains just as literally, unsolved. Because this early universe was a dense, evenly filled plasma rather than the empty vacuum space would later become, it was capable of carrying something that vacuum cannot: sound. Waves of pressure moved through this hot, thick medium in a phenomenon physicists call baryon acoustic oscillations, deep, resonant compressions rippling outward through the plasma the way sound moves through water, only far faster and at a scale spanning the entire observable universe. These oscillations began almost immediately, within the first second, meaning the newborn universe was, in a very real sense, ringing. A human ear could not have registered any of it. The frequencies involved sit far below the range of human hearing, deep and slow in a way that would register only as pressure, a physical sensation without an accompanying sound. Scientists who study these oscillations today, using their imprint on the distribution of galaxies across the sky, have taken the underlying frequencies and shifted them upward into a range human hearing can process. Rendered this way, through a computer rather than through air and eardrum, the result resembles static, or a low, continuous roar, closer to distant surf than to anything resembling an explosion. It is worth sitting with that image for a moment. The birth of the entire universe, translated into sound, resembles less a bang than a wave breaking somewhere just out of sight. There is a certain fittingness to that. The name Big Bang was never meant as a literal description, and was in fact coined somewhat dismissively by a scientist who favored a competing theory. The event itself, at the scale a human observer could actually register it, was less a bang and more a deep, sustained pressure, felt through the body rather than heard through the ears. A hum too vast and too low to register as sound in any conventional sense, even while it was, in the most technical sense available, the loudest event that has ever occurred. Sound is only part of what this earliest universe produced. There is also the question of light and of color, since the popular image of the Big Bang as a blinding flash of white or orange light does not match what the physics actually describes. The very first light released in this era was not visible light at all, but high-energy gamma radiation, a wavelength far too short for the human eye to register under any circumstances. In the strictest sense, the birth of the universe began in a color that has no name in ordinary human vocabulary, because no human eye has ever been built to perceive it. As the universe continued expanding in the moments and years that followed, it also cooled, and that cooling gradually shifted the character of the light, filling it. The invisible gamma radiation of the earliest instant gradually gave way, over time, to something closer to visible wavelengths, edging toward a warm, peach-colored glow, before eventually fading further still. This shift did not happen instantly. It unfolded gradually as the universe's own expansion stretched its light toward longer, cooler wavelengths. The same underlying mechanism responsible for the redshift astronomers measure in distant galaxies today, only now happening to the light of the universe as a whole, rather than to any single object within it. Standing inside this moment, granted the narrative exception that allows you to witness it at all, the experience would layer several impossible sensations on top of each other at once. A pressure with no air behind it, pressing directly against the particles that make up your body rather than against your skin. A silence that is not empty, but simply pitched too low for human hearing to register, even as the plasma around you rings with waves spanning the width of what will eventually become the observable universe. A light too energetic to see, filling a space that had, only a fraction of a second earlier, not existed as space at all. None of these sensations arrive one after another, the way sensations usually do. They arrive together, compressed into an instant so brief, it barely qualifies as a duration. It would be easy to imagine this moment as violent, in the way an explosion is violent, chaotic, and directionless. The evidence suggests something closer to the opposite. Despite the almost incomprehensible energies involved, this earliest universe was, on the whole, remarkably smooth and evenly distributed, its temperature varying by only the faintest of margins from one region to the next. That evenness matters enormously for everything that follows. Without it, matter would have clumped too unevenly, and the ordered structures of galaxies and stars that fill the sky today might never have had the conditions needed to form. The birth of the universe was not merely powerful. It was, in its own strange and thunderous way, remarkably well balanced. A foundation steady enough to build 13.8 billion years of everything else on top of it. What follows this instant is not another sudden event, but the opposite. A long, slow stretch of nearly 400,000 years in which nothing much appears to change to the casual eye, even as the universe quietly cools toward a threshold that will, for the first time, allow light to travel freely instead of being trapped within the dense plasma, still filling every direction you can look. It is a strange feature of this journey that its most violent moment, by any reasonable measure, the single most energetic event that has ever occurred, gives way immediately to one of its quietest. There is no gradual settling, no slow fade from chaos to calm. There is simply an instant of unimaginable transformation, followed at once by a plasma that, while still ferociously hot by any ordinary standard, has already begun the long, patient work of expanding and cooling towards something that will eventually resemble a universe capable of being looked at, rather than merely existed within. That transition, from violence to patience, from an instant to an epoch, is a pattern worth noticing, because it will repeat itself again and again across the billions of years still ahead in this story. A brief, transformative event, followed by a long, quiet stretch in which the universe simply continues doing what it has already been set in motion to do. The Big Bang itself was the first and most extreme example of that pattern, but far from the last. For the next stretch of this journey, roughly 380,000 years, very little would appear to happen, at least on the surface. No stars yet exist, no galaxies have formed. There is only a vast, glowing plasma, cooling gradually as the universe continues its steady expansion. It is tempting to treat a span like this as empty time, a gap between the dramatic instant of the Big Bang and the eventual formation of everything recognizable. That would be a mistake. This stretch of near nothing is where the universe first became something you could, in principle, look at. For most of these 380,000 years, the universe existed in a state physicists describe as opaque, a condition worth pausing on because it means something quite specific. Free electrons, not yet bound into atoms, filled the plasma in enormous numbers, and photons of light, attempting to travel through that plasma, could not move in a straight line for any meaningful distance. They would immediately collide with an electron, scatter in a new direction, travel a short distance, and collide again. This scattering repeated itself constantly, trapping light within the plasma, the way fog traps a beam from a flashlight, scattering it in every direction, rather than allowing it to travel cleanly from source to observer. Standing inside this stage of the journey, the effect would resemble being inside an enormous, glowing cloud, bright but directionless, with no clear source of light and no clear shadow cast by anything, because nothing near you would be receiving light in straight, traceable lines. It is one of the few stretches of this journey where the word disorienting undersells the experience. There would be brightness on every side, and yet nothing resembling sight as it is normally understood. No edges, no distances, no way to judge how far anything actually sat from anything else. A useful, if imperfect, comparison involves standing in the middle of a thick bank of fog on an overcast morning, holding a lit lamp at arm's length. The light from that lamp does not travel outward in a clean beam. It scatters in every direction almost immediately, filling the air around the lamp with a soft, directionless glow, rather than casting the kind of sharp, traceable beam a flashlight produces on a clear night. Now imagine that same fog extending not for a few dozen meters, but across the entire universe, every particle of moisture replaced by a free electron, and every photon of light undergoing that same scattering, over and over, for 380,000 years without pause. The comparison is imperfect in scale, wildly imperfect, but it captures something true about the texture of the experience: brightness without direction, illumination without the ability to actually see anything by it. This condition persisted because the plasma remained too hot for electrons to settle into stable orbits around atomic nuclei. Even though protons and light nuclei had already formed within the first few minutes after the Big Bang, the surrounding temperature was still high enough that any electron attempting to bind to a nucleus would almost immediately be knocked loose again by a passing photon or a collision with another particle. The universe, in effect, was too energetic to allow atoms, in their complete and stable form, to exist for any meaningful length of time. Slowly, though, as the universe continued to expand, it also continued to cool, the same steady process that had been unfolding since the earliest instant. Roughly 380,000 years after the beginning, the temperature dropped low enough, to around 3,000 degrees Celsius, that electrons could finally settle into stable orbits around nuclei without immediately being stripped away again. This moment carries the name recombination, though the name is slightly misleading, since electrons and nuclei had never been bound together before this point. It might be more accurate to call it simply combination, the first true formation of complete, stable atoms anywhere in the universe's history. The effect of this moment on light was immediate and dramatic. With electrons now bound into atoms, rather than drifting freely through the plasma, there was suddenly nothing left to scatter photons in every direction. Light, for the first time since the universe began, could travel in a straight, unobstructed line. The fog that had filled every direction for 380,000 years lifted, not gradually, but essentially all at once, across the entire universe simultaneously. If you were watching from within this moment, the effect would resemble the sudden clearing of a heavy mist, revealing, all at once, a glowing landscape stretching outward as far as light itself was now free to travel. The color of that landscape would not have matched the fiery orange typically associated with explosions and fires on Earth. In its earliest visible state, the universe glowed with a warm, bright orange tone, closer to the light cast by an incandescent bulb in a dining room than to the harsh glare of a fire. As the universe continued expanding and cooling in the years that followed, that warm glow gradually shifted, fading toward red and eventually toward black, as the light stretched into wavelengths beyond what the human eye could register. Today, this ancient light still exists, redshifted over billions of years into the microwave portion of the spectrum, far too long a wavelength for human eyes to see directly at all. Standing in this newly transparent universe, granted the same narrative exception that has carried you this far, the sensation would be closer to standing inside a vast, warmly lit room than to witnessing anything resembling a violent birth. The heat of the earlier plasma has faded considerably by this point, though it would still be far beyond anything survivable, and the light filling every direction would carry that same warm orange quality, gentle rather than harsh, closer to late afternoon sunlight, filtered through haze than to the glare of direct noon sun. There is a strange calm to this stage of the journey. A universe finally settled enough to be seen, even though nothing yet exists within it worth pointing a telescope toward. Astronomers, many years later, would calculate the average color of the entire universe across all of cosmic history and give it an almost domestic name: cosmic latte, a pale, warm beige, not far removed from the color filling the space around you at this very moment in the journey. Long before that average had fully settled into place, this ancient light has a name: the cosmic microwave background, often shortened to the letters CMB. It is not, strictly speaking, a leftover glow from the Big Bang itself, though it is sometimes described that way in casual conversation. It is more precisely a snapshot of this specific moment, 380,000 years after the beginning, the exact instant the universe became transparent enough for light to travel freely. That light has been traveling ever since, filling every direction of the sky, arriving today as a faint, nearly uniform microwave signal, present in every part of the observable universe, including the empty space directly above wherever you happen to be standing right now. There is a small, almost charming detail connected to this discovery. A portion of the static, visible on an old analog television, tuned between channels, comes from this same ancient light. Roughly 1% of that snowy interference is the cosmic microwave background itself, a signal from 380,000 years after the beginning of the universe, arriving in an ordinary living room and displaying itself as nothing more than background noise on an outdated screen. Most people who ever saw that static had no idea they were looking, in a very real sense, at the oldest light in existence. The discovery of this ancient light did not happen through a mission specifically designed to find it. In the 1960s, two radio engineers working with a sensitive antenna in New Jersey kept detecting a faint, uniform hiss of interference they could not explain. They checked the equipment for faults, cleared out pigeon droppings that had accumulated inside the antenna, and still the signal remained, coming equally from every direction of the sky, day and night, regardless of the season. The antenna itself had originally been built for satellite communication, a large, horn-shaped instrument sensitive enough to pick up faint signals bounced off early communications satellites, and it was this same sensitivity that made it capable of detecting a signal nobody had intentionally sent it looking for. It took collaboration with a nearby team of physicists who had been independently predicting that exactly this kind of leftover radiation should exist if the universe had indeed begun in a hot, dense state, to realize what the engineers had stumbled onto. That accidental discovery became one of the strongest pieces of evidence ever found for the Big Bang, and it effectively settled a long-running scientific rivalry that had persisted for years. That rivalry was between the Big Bang model and a competing idea called the steady-state theory, which proposed that the universe had no beginning at all, and instead existed eternally in roughly its current form, with new matter continuously created to fill the gaps left by ongoing expansion. It was, in fact, a prominent advocate of the steady-state theory who first used the term Big Bang. During a radio broadcast, intending the phrase somewhat dismissively, as a way of mocking what he considered an implausible idea. The name stuck regardless, adopted eventually even by scientists who fully accepted the theory it was coined to ridicule. The discovery of the cosmic microwave background, a direct, physical remnant of a hot early universe, gave the Big Bang model a decisive advantage the steady-state theory could never adequately explain, and within a few years, scientific consensus shifted firmly in its favor. In the decades since that accidental discovery, 3 major space missions, launched years apart, have mapped this ancient light with steadily increasing precision. The first, a satellite named COBE, launched in 1989, produced the earliest confirmed measurements of the tiny temperature variations scattered across the sky, a result significant enough to eventually earn its lead researchers a share of the Nobel Prize in Physics. A second mission, WMAP, launched in 2001, sharpened that picture considerably, mapping the sky in far greater detail and allowing scientists to pin down the universe's age at 13.8 billion years, with a level of precision that would have seemed unreachable only a decade earlier. A third mission, the Planck satellite, launched in 2009, refined the picture further still, producing the most detailed all-sky map of this ancient light created to date. Each mission built directly on the work of the one before it, turning what began as an unexplained hiss of static in a New Jersey antenna into one of the most thoroughly measured signals in all of physics, a direct window into a moment 380,000 years after the beginning of everything. Scientists have a specific name for the moment captured in this ancient light, the surface of last scattering, a phrase describing the precise point at which photons collided with an electron for the final time before traveling freely onward, uninterrupted, for the following 13.8 billion years. It functions almost like a wall, the furthest back in time that light itself can carry direct information, since everything before. This moment was hidden behind the same opaque fog that made the early universe impossible to see through. Whatever happened before the surface of last scattering, all the way back through nucleosynthesis, the quark-gluon plasma, and inflation itself, has to be reconstructed indirectly through particle physics, through the composition of the oldest matter, and through careful extrapolation, rather than through any direct photograph. The cosmic microwave background is, in this sense, both the earliest image available and a genuine boundary, a curtain drawn across everything that came before it. Scientists have studied this ancient light with extraordinary precision, mapping tiny variations in its temperature across the sky, differences measured in millionths of a degree. Those variations, subtle as they are, mark the earliest seeds of structure in the universe, the faint overdensities that would, over the following hundreds of millions of years, draw in more and more surrounding matter through gravity, slowly building the first stars and eventually the first galaxies. Without those tiny irregularities, first present in the plasma long before recombination and then locked permanently into the pattern of the cosmic microwave background, the universe might have remained forever smooth and empty, with nothing ever gathering densely enough to ignite into starlight. The connection between this faint, ancient pattern and the modern night sky is not merely poetic. Astronomers have directly compared maps of the cosmic microwave background's temperature variations with maps of galaxy distribution across the present-day universe and found a genuine correspondence. The regions that were very slightly denser 380,000 years after the Big Bang correspond, billions of years later, to the regions containing the greatest concentration of galaxies today, while the regions that were very slightly less dense correspond to the vast, nearly empty voids that separate one filament of galaxies from the next. The faint speckled pattern visible in a map of the cosmic microwave background is, in a very real sense, a blueprint, sketched out within the first fraction of a second of the universe's existence, and then patiently built upon by gravity for the following 13.8 billion years. Standing at this point in the journey, watching the fog lift and the first true light of the universe spread outward in every direction, it is worth remembering how long a wait still lies ahead before anything resembling a star appears. 380,000 years is an almost unimaginable stretch of time by ordinary standards, and yet, measured against the full 13.8 billion year span of cosmic history, it amounts to little more than the very first heartbeat. The universe has only just become visible. It has not yet become interesting to look at. What follows this clearing is, in its own way, a return to darkness, though a darkness of a different and quieter character than anything encountered so far. The plasma's glow will continue to fade as the universe expands, and no new source of light will rise to take its place for a very long time. The universe, having just gained the ability to be seen, is about to spend the better part of 200 million years with almost nothing worth seeing at all. That stretch of near total darkness might sound, on its surface, like an empty pause in an otherwise eventful story. It is closer to the opposite. It is the quiet, unglamorous span of time during which gravity does its most essential, least visible work, patiently drawing the faint irregularities left over from the earliest universe into denser and denser pockets of gas, laying the groundwork for every star, every galaxy, and every planet that will eventually fill the sky. Nothing about that process announces itself. It simply happens, slowly, in the dark, until, at last, it doesn't. What follows the clearing of the ancient fog is not another dramatic event, but a long and mostly uneventful stretch of waiting, one that would test the patience of anyone standing through it in person. For roughly 200 million years after the universe became transparent, nothing resembling a star exists anywhere. There is only hydrogen and helium, the two simplest elements, drifting through space in slowly thickening clouds, along with the faint, still cooling glow of the light released during recombination. This period carries a fittingly quiet name among astronomers: the Cosmic Dark Ages. It is dark in a very literal sense, since the glowing plasma from earlier in the universe's history has faded, and no stars yet exist to replace it as a source of light. The universe, during this stretch, is not empty, but it is dim, filled with gas that has not yet gathered densely enough anywhere to ignite. Gravity, working patiently across those 200 million years, slowly draws the faint irregularities left over from the earliest moments of the universe into denser and denser clumps, clouds of hydrogen and helium collapsing gradually under their own weight. Standing through this stretch of the journey would mean standing through an almost total absence of anything to look at. No pinpoints of starlight would break the darkness. No glowing clouds would offer even the diffuse illumination of the earlier plasma era. There would only be a vast, cooling emptiness, threaded here and there with faint, slowly thickening clouds of gas, invisible without instruments capable of detecting matter that gives off no light of its own. Astronomers have never observed this era directly, for the simple reason that it produced nothing bright enough to see. Everything known about the cosmic dark ages comes from careful modeling, built on the physics of gravity and gas rather than on any direct image, an honest gap in an otherwise well-documented history, waiting on future instruments sensitive enough to detect the faint radio signals these clouds are thought to emit. Eventually, in scattered pockets across this vast, dim universe, enough gas gathers in a single place to reach the temperature and pressure needed to ignite nuclear fusion at its core. The first stars begin to form. They do not resemble the sun, or most of the stars visible in a modern night sky. Because they formed from gas containing nothing but hydrogen and helium, with none of the heavier elements that later generations of stars would inherit, these earliest stars are thought to have been enormous, some many times more massive than the sun, burning through their nuclear fuel at an extraordinary rate. That combination, immense mass and a hunger for fuel, meant these first stars lived short, violent lives by stellar standards, existing for perhaps only a few million years before exhausting their cores and collapsing. Without the heavier elements that help modern stars cool and fragment into smaller pieces while forming, these earliest stellar nurseries tended to collapse into a smaller number of much larger stars, rather than the varied mix of star sizes seen in star-forming regions today. For an observer who has just spent 200 million years standing through absolute darkness, the ignition of even a single one of these first stars would carry a weight that later starlight, arriving into an already bright and familiar sky, could never quite match. A single point of light appearing in a universe that has never once produced light of its own accord is not a subtle event. It marks the precise moment the universe stopped being merely warm leftover matter and became, for the first time, a place capable of generating its own light through the same process that still powers every star visible from Earth tonight. Scattered and rare at first, these points of light would begin to multiply across the following tens of millions of years, gradually filling in what had been, until that point, an unbroken darkness. Those first stars did more than simply provide light. The gas filling the universe at this stage consisted mostly of neutral hydrogen, atoms with their electrons still bound in place, largely transparent to visible light but still capable of absorbing certain other wavelengths. The intense, ultraviolet radiation pouring out of these massive, short-lived first stars gradually stripped electrons back off that neutral hydrogen, a process astronomers call reionization, spreading outward from each new star and each new pocket of star formation like ripples expanding across still water. Over the following several hundred million years, these overlapping ripples eventually merged, reionizing nearly all the hydrogen gas filling the universe, and clearing the way for light to travel across vast distances, largely unobstructed, much as it had after recombination, though through an entirely different mechanism and for an entirely different reason. When those first giant stars died, many of them did so in spectacular fashion, as supernovae, explosions so bright they could, for a brief period, outshine the combined light of every other star in their surroundings. These explosions mattered for reasons that go well beyond the light they released. Deep within the cores of those dying stars, nuclear fusion had been forging elements heavier than hydrogen and helium, carbon, oxygen, nitrogen, and eventually iron, elements that simply did not exist anywhere in the universe before this point. When those stars exploded, they scattered those newly forged elements outward into the surrounding gas, seeding the universe, for the very first time, with the raw materials needed to eventually build planets, and much later, living bodies. It is worth pausing on that fact directly, because it tends to sound more poetic than it is usually given credit for being, without needing any exaggeration to make the point land. The calcium in bone, the oxygen carried through blood, the carbon forming the backbone of every living cell, were forged inside the cores of stars that lived and died long before the Sun, or Earth, or anything resembling a solar system existed at all. This is not a metaphor or a loose comparison. It is a straightforward description of where those specific atoms originated, traced back through supernovae that scattered them across space, eventually to be drawn together, billions of years later, into the clouds of gas and dust that would form new stars, new planets, and eventually, a body capable of standing here and considering the question at all. Not every element found in the human body traces its origin to an exploding star, however. Iron marks something close to a practical ceiling for the fusion process happening inside an ordinary star's core, the heaviest element a star can produce through fusion while still releasing energy in the process. Elements heavier than iron, including the gold and silver worn as jewelry, and the iodine required by the thyroid gland to function correctly, demand a far more violent origin than even a supernova can typically provide. The leading candidate for their creation involves the collision of two neutron stars, the collapsed, ultra-dense remnants left behind by certain supernovae, spiraling into each other and merging in an event releasing so much energy that heavier nuclei can be forged in the resulting chaos before scattering outward into space. Such a collision was directly observed for the first time only in 2017, detected through gravitational waves rippling across space and confirmed shortly afterward by telescopes around the world. A rare case of watching, almost in real time, the same kind of process responsible for scattering a portion of the very atoms that make up a human body. As this process repeated itself across hundreds of millions of years, generation after generation of stars living and dying, the concentration of heavier elements scattered through the universe slowly climbed. Meanwhile, gravity continued its patient work at a larger scale as well. Roughly 400 million years after the Big Bang, the first galaxies began to take shape. Loose collections of stars, gas, and dust drawn together by their combined gravity into structures that would continue growing and merging for billions of years afterward. These earliest galaxies were smaller and less organized than the sweeping spirals familiar from modern astronomy, closer to irregular clumps than to the elegant, pinwheel structures that would eventually form. Over time, through repeated mergers and continued accumulation of gas, some of these early structures would grow into the grand spiral and elliptical galaxies that fill the night sky today. The Milky Way itself began assembling not long after those first galaxies appeared, though it would take billions of years and countless mergers with smaller neighboring galaxies to reach anything resembling its current spiral shape. Even today, that assembly is not entirely finished. Smaller dwarf galaxies continue to be drawn in and absorbed by the Milky Way's gravity, a slow, ongoing process that has been unfolding for most of the galaxy's existence and shows no sign of having concluded. The Sun and its planets occupy a fairly ordinary position within one of the Milky Way's spiral arms, roughly halfway out from the galactic center, in a region with no particular claim to significance beyond the fact that conditions there eventually prove suitable for a star, and later a planet, and later still, a species capable of tracing its own origin back through this entire journey. In recent years, powerful space telescopes capable of detecting extremely faint, distant light have found galaxies from this early era that appear larger and more developed than older models predicted they should be, given how little time had passed since the Big Bang. This has prompted genuine, ongoing debate within the astronomical community. Some researchers proposing that early galaxies formed and grew more efficiently than previously assumed. Others suggesting that the standard model of cosmic structure formation may need meaningful revision. Neither position has settled the question completely. It stands, at present, as one of the more active areas of research in modern cosmology, a reminder that even a history as thoroughly studied as this one still contains real, unresolved edges. The wait for anything resembling the solar system stretches on considerably longer still. It would take 9.3 billion years, nearly 2/3 of the universe's entire history up to the present day, before the specific cloud of gas and dust that would become the sun finally collapsed under its own gravity and ignited. That cloud itself was not primordial, untouched material left over from the earliest universe. It was enriched by billions of years of previous stellar generations, carrying within it the heavier elements forged and scattered by countless earlier supernovae, elements that would go on to form not just the sun, but the planets orbiting it, Earth included. From the ignition of the sun, only another few 100 million years would pass before the swirling disk of leftover gas and dust surrounding it began clumping together into planets, Earth among them, coalescing out of debris that had itself once been part of dying stars. Not long after Earth itself took shape, a collision with another young planetary body, roughly the size of Mars, is thought to have thrown a vast quantity of debris into orbit, debris that gradually gathered itself into the moon still visible overhead most nights. And from there, another 4.6 billion years, the entire span of Earth's own geological and biological history, separates that moment from the one you are standing in right now, reading or listening to these words. Returning, at last, to the present day closes the first half of this journey. The universe surrounding you now looks nothing like the glowing plasma, the dark quiet centuries, or the scattered first galaxies that filled the stretches just covered. It looks instead like an ordinary night sky, familiar and, on the surface, unremarkable, populated by billions of galaxies, each containing billions of stars. Each of those stars descended, in some fashion, from that same original singularity, compressed once into a space smaller than a proton. It is worth taking a moment to register the scale of what has just been covered before moving forward into the second half of this journey. Nearly 14 billion years, condensed into a handful of chapters, spanning a transition from a point smaller than anything visible to the unaided eye, to a universe filled with more galaxies than there are grains of sand on every beach on Earth combined. Every structure encountered along the way, every star, every supernova, every galaxy, traces back, without exception, to the same singular origin. That is the answer to the first question this journey set out to explore. Yes, in every atom that makes up the body reading these words, there is a direct, physical connection to the earliest instant of the universe's existence. What remains is the second, stranger question, the one this journey has been building toward from its very first sentence. Notice, too, what this first half of the journey did not require. At no point was it necessary to invoke anything beyond ordinary, well-tested physics, gravity, thermodynamics, nuclear fusion, the behavior of light and plasma under extreme conditions. Every stage, from the reversed unraveling of galaxies to the ignition of the first stars, rests on measurements that can be independently checked, repeated by different research teams using different instruments, and confirmed against each other. That solidity is worth appreciating on its own terms before stepping past it into the considerably less certain territory that lies ahead. There is one more detail worth carrying back with you from this long return journey. a discovery that complicates the tidy picture of an expansion simply continuing at a steady pace from the initial Big Bang onward. In the late 1990s, two separate teams of astronomers, studying a particular class of exploding stars whose brightness could be measured with unusual precision, expected to find that the universe's expansion was gradually slowing down, pulled inward by the collective gravity of everything within it. Instead, both teams found the opposite. The most distant of these exploding stars appeared dimmer than expected, meaning they were farther away than a steadily expanding universe would predict, evidence that the expansion itself was speeding up rather than slowing down. The discovery was unexpected enough and confirmed carefully enough by both independent teams that it was eventually recognized with one of the highest honors available in the sciences. The universe, in other words, is not merely expanding, it is expanding at an accelerating rate. Something is driving that acceleration, some form of energy that pushes space apart faster and faster as time goes on, and at present, nobody knows with any certainty what that something actually is. Scientists have given it a placeholder name, dark energy, useful for referring to the phenomenon in conversation, but honest in its admission that the underlying cause remains unidentified. It is one of the larger open questions sitting quietly at the edge of an otherwise remarkably well-understood cosmic history, a reminder that even after tracing this entire journey from the singularity to the present day, there remain gaps in the record that no one has yet been able to close. Everything covered so far in this journey, the reversed unraveling of galaxies, the crush toward a singularity smaller than a proton, the instant of expansion, the long fog, the dark ages, and the slow arrival of starlight, rests on solid ground. Not certainty in every detail, but solid ground nonetheless, supported by measurements that can be checked, repeated, and confirmed across independent lines of evidence. The redshift of galaxies, the composition of the oldest stars, the cosmic microwave background itself, all point toward the same basic picture, a universe that began in a hot, dense state roughly 13.8 billion years ago. What lies before that state is a different kind of territory entirely. This is the second half of tonight's journey, the part where the ground grows considerably less solid, and where honesty requires admitting, clearly and without embarrassment, that nobody currently knows the answer. There are, however, several serious ideas proposed by working physicists rather than speculative outsiders that attempt to address what, if anything, existed before the singularity. None of them have been confirmed. None of them can currently be tested with the instruments available today, but each of them is worth walking through carefully, because each represents a genuine attempt to extend the story past the point where direct evidence runs out. Before walking through those ideas, it is worth sitting with a possibility that some physicists take just as seriously as any specific theory, that the question of what came before the Big Bang may not be a well-formed question at all. If time itself began at the same instant as space, then the word before, which normally describes an earlier point along a timeline, may simply have nothing to attach to. There would be no earlier point, not because it has been lost or forgotten, but because the very structure that makes earlier and later meaningful concepts did not yet exist. A commonly used comparison involves standing at the North Pole and asking what lies further north. The question sounds grammatically sound, structured the same way any other direction-based question is structured. But it fails to correspond to anything real, because north, at that specific point, has run out of meaning to describe. Some physicists suspect that asking what came before the Big Bang may be a similar kind of category error, a well-formed sentence pointing at a question that does not actually exist. Others disagree and think the question remains meaningful, simply unanswered. Both positions are held by serious researchers, and neither has been settled. The first idea carries the name the Big Bounce. It proposes that the universe we know is not a singular, one-time event, but rather one cycle in an ongoing, perhaps endless, sequence. In this model, a previous universe having expanded for billions or trillions of years, eventually begins to slow, then reverses, collapsing back in on itself the way a stretched spring eventually snaps back toward its resting shape. Rather than collapsing all the way down into a true singularity and simply ending, the theory proposes that some unknown physical process halts the collapse at an extremely small but non-zero size, and the whole process rebounds outward again. A new expansion, a new Big Bang, beginning from the compressed remains of the one before it. Under this model, the Big Bang you have just traveled through would not be the beginning of everything, but simply the most recent bounce in a cycle that may have been repeating for a length of time with no clear starting point at all. The appeal of the Big Bounce model lies partly in what it avoids. A universe with a true singular beginning raises an uncomfortable question about what, if anything, came before that beginning, and traditional physics has no natural tools for answering a question like that. A universe that bounces endlessly sidesteps the question by removing the need for a true first moment altogether. Every bang is preceded by a bounce, and every bounce is preceded by an earlier phase of collapse, stretching backward, in principle, without any absolute starting point. The difficulty, and it is a significant one, lies in the physics required to make a bounce actually work. Standard models of gravity, including general relativity, predict that a collapsing universe should proceed all the way down to a true singularity, not stop partway in reverse. Making the bounce work requires new physics, most often drawn from attempts to merge gravity with quantum mechanics, precisely the same unresolved territory that makes the Planck epoch so difficult to describe with confidence. One specific line of research, called loop quantum cosmology, proposes that space itself has a smallest possible unit, a kind of grain beneath which it cannot be subdivided any further, and that this graininess produces an outward quantum pressure once matter is compressed past a certain threshold, strong enough to halt a collapse and reverse it before a true singularity ever forms. The mathematics behind this approach has produced some promising internal consistency, but like every other proposal in this chapter, it remains without direct observational confirmation. The Big Bounce, in any of its specific forms, remains a serious, actively studied idea, but it is far from a settled one. A second idea approaches the question from a different angle entirely, building on a concept already introduced earlier in this journey: inflation, the extraordinarily rapid expansion that occurred in the first fraction of a second after the singularity. Standard inflation describes a single brief burst of expansion that transitioned into the hot, dense plasma that would go on to become the Big Bang as usually described. A related, but more expansive version of this idea, called eternal inflation, proposes that this rapid, inflating expansion does not necessarily stop everywhere at once. Instead, it may continue indefinitely across some larger, still inflating background, with our own universe representing just one region, one bubble, where the inflation happened to stop, cool, and settle into the ordinary matter and energy that would go on to build stars and galaxies. Under eternal inflation, other bubbles, other regions where inflation similarly halted and gave rise to their own separate, self-contained universes would exist as well, scattered across an inflating background, too vast and too fast, expanding for light to ever travel between one bubble and another. This picture is sometimes referred to, somewhat loosely, as a multiverse, though the term covers a range of different theoretical proposals rather than a single, unified idea. If eternal inflation is correct, then the Big Bang this journey has traced was never the beginning of everything in any absolute sense. It was simply the moment inflation stopped in this particular region, one bubble among an unknown, possibly unlimited number of others, each with its own Big Bang, its own 13.8 billion years, or however many billions of years each bubble's own physics happens to allow. It is worth being honest about the limits of this idea as well. Eternal inflation is a mathematically consistent extension of inflationary theory, and many physicists take it seriously as a natural consequence of models that already explain other, well-tested features of the early universe. But by its very nature, if other bubbles exist, they lie forever beyond the reach of any signal that could ever reach us, given how quickly the space between bubbles is thought to expand. That makes direct confirmation, in the ordinary scientific sense of gathering evidence and testing predictions, effectively impossible. Eternal inflation remains a serious hypothesis, grounded in real physics, but one that may never move past the category of hypothesis, simply because the evidence needed to confirm or rule it out may not be obtainable even in principle. A third and stranger idea approaches the question from an entirely different direction, starting not from what came before the Big Bang, but from what lies beyond the edge of the universe we can currently observe. If you were to travel to the very edge of the observable universe and try to look beyond it, the honest answer, under the standard picture, is that there is nothing to see, not even darkness, because the space required for anything, light included, to exist there simply has not been created yet. The universe is not expanding into a larger, pre-existing empty space the way a balloon expands into the air of a room. It is generating new space as it grows, and beyond its current edge, there is, in the most literal sense, no space at all, not empty, just absent. Some physicists have proposed a stranger alternative to this picture, that our entire universe exists inside the interior of an extremely large black hole, formed within some larger, outer universe we have no access to and no way of observing. Under this model, what we experience as the Big Bang would correspond to the formation of that black hole from the outside perspective, and what we experience as the ongoing expansion of our universe would correspond to conditions inside the black hole's interior, a region that behaves, according to some interpretations of general relativity, less like a point of no return and more like the seed of an entirely new, self-contained universe. This idea remains highly speculative, resting on theoretical work rather than direct evidence, and most cosmologists treat it as one interesting possibility among several, rather than a leading contender. Some versions of this proposal note an appealing symmetry. If our universe sits inside a black hole formed in some outer, parent universe, and if black holes within our own universe might, in turn, give rise to new universes of their own, the picture that emerges resembles a kind of cosmic reproduction, universes nested within universes, each generation seeding the next through the same gravitational collapse that, within our own universe, simply produces the black holes astronomers already study directly. It is a striking image, and one that has drawn genuine interest from serious researchers. But it remains, at present, firmly in the category of hypothesis rather than established science. It is included here not because it is well established, but because it illustrates just how open this particular question remains, and how differently serious researchers have approached trying to answer it. A fourth idea, related to the Big Bounce but distinct from it, comes from a proposal called conformal cyclic cosmology, developed by a mathematical physicist who spent decades working on the geometry of space and time. This model imagines not a single universe bouncing back and forth between collapse and expansion, but an endless sequence of entirely separate cosmic cycles, or aeons, each one beginning with its own Big Bang and ending unimaginably far in the future, not in a fiery collapse, but in a cold, stretched-out state where all matter has decayed and only the faintest, most spread-out radiation remains. According to this proposal, the geometry of that final, maximally expanded state is mathematically equivalent to the geometry of a fresh Big Bang, allowing one aeon to flow directly into the next without any true singularity, acting as a barrier between them. The physicist behind this idea has claimed to identify faint circular patterns in the cosmic microwave background that might represent the imprint of black hole collisions from the previous aeon, bleeding through into this one. Other researchers who examined the same data reached a different conclusion, finding no statistically significant evidence for such patterns once ordinary statistical noise was properly accounted for. The disagreement remains unresolved, a reminder that even claims of possible evidence for what came before the Big Bang tend to dissolve, on closer inspection, back into the same uncertainty surrounding every other idea in this chapter. This pattern, a claim of possible evidence followed by careful, often deflating scrutiny, repeats itself across nearly every serious attempt to test these theories. It is, in its own way, a healthy sign rather than a discouraging one. It means the scientific process is functioning as intended, treating extraordinary claims about the origin of the universe with the same skepticism applied to any other scientific claim, rather than accepting them simply because they would make for a satisfying answer to an old and difficult question. None of these ideas, the Big Bounce, eternal inflation, the black hole universe, or conformal cyclic cosmology, can currently be tested in a way that would allow scientists to confirm one and rule out the others. Each rests on extending known physics into a regime, the Planck epoch and whatever, if anything, preceded it, where the tools required to make confident predictions simply do not yet exist. This is not a failure of imagination or effort. It reflects an honest limit, one that sits at the outer edge of what current instruments and current theory can reach. The record, at this boundary, is genuinely incomplete, and it may remain incomplete for a very long time, regardless of how the underlying question is eventually resolved, if it ever is. It is worth noting, too, that these four ideas are not the only proposals that have been made. Other researchers have suggested variations involving extra spatial dimensions folding and unfolding, or scenarios drawn from string theory, in which our universe formed from the collision of two higher dimensional membranes drifting through a larger space. Each of these additional proposals faces the same basic obstacle as the four described here, a genuine absence of evidence capable of distinguishing it from its competitors. Listing every variation would turn this chapter into a catalog rather than a journey, so only the most discussed and most carefully studied ideas have been included. The broader point holds regardless of how many specific proposals exist. There is no shortage of ideas about what came before the Big Bang, and there is, at the same time, no way, currently, to know which of them, if any, is correct. That may, in the end, be an unsatisfying place to arrive after such a long journey. It is worth sitting with that dissatisfaction honestly, rather than smoothing it over with false confidence. Science does not owe anyone a tidy answer simply because the question feels important, and the question of what came before the beginning of everything is about as important as questions get. What science does owe, and what this journey has tried to provide, is an honest account of exactly how far the evidence currently reaches, and an equally honest acknowledgement of where that evidence runs out, leaving genuine uncertainty in its place, rather than a comfortable but unearned conclusion. There is a particular kind of patience required to sit with a question this large without forcing a premature answer onto it. It is the same patience this journey has asked of you at every stage. Through billions of years of unraveling galaxies, through a crush of heat and pressure with no true precedent, through a fog that took 380,000 years to lift, and through 200 million years of near-total darkness before the first star finally lit. The question of what came before the Big Bang simply asks for a little more of that same patience, applied to a boundary that may never fully resolve, at least not within any timescale relevant to a single human life. Perhaps a future generation of physicists will find a way past this boundary. Some new instrument, some new mathematical framework, capable of testing what remains, for now, untestable. Perhaps the boundary itself is permanent, a genuine limit on what any observer inside this universe can ever know about what, if anything, existed before it. Both possibilities remain open. Neither can be ruled out tonight, and neither needs to be resolved before the journey draws to its close. What can be said with more confidence is this: whatever did, or did not exist before the singularity, the universe that emerged from it, expanding, cooling, forging stars and heavy elements across billions of years, eventually produced every atom that makes up the body reading or listening to these words right now. That much is not speculation. It is measured, checked, and about as well confirmed as anything in modern science manages to be. The question of what came before remains open. The question of what came after, the long, patient, 13.8 billion year unfolding that built stars and galaxies, and eventually a mind capable of asking where any of it came from, has, by comparison, a remarkably clear answer. Zoom out far enough, and this entire journey collapses into a single, quiet fact. 13.8 billion years ago, everything that exists was folded into a point smaller than anything the eye could register, and from that point came galaxies, stars, planets, and eventually, on one small world orbiting one ordinary star, a body capable of tracing the whole story back to its beginning. That is not a small thing to hold on to. It does not require exaggeration or hype to feel its weight. The plain facts carry enough weight on their own. What came before that beginning remains genuinely unknown. Not unknown in the sense of a puzzle waiting for its obvious solution, the way a difficult math problem sits waiting for the right method to unlock it, but unknown in a deeper, more honest sense, a question that may sit permanently beyond the reach of any instrument or theory available to a species built from the debris of exploded stars, looking backward across the very history that built it. The Big Bounce, eternal inflation, the black hole universe, conformal cyclic cosmology, each offers a way of imagining what might lie on the other side of that boundary. None of them offers proof. That absence of proof is not a failure of this journey, or of the science behind it. It is simply where the evidence currently runs out, honestly reported rather than papered over with false certainty. There is something worth carrying forward from this uncertainty, rather than something to resolve before setting it down for the night. Every atom in a human body was forged inside a star that lived and died long before the sun existed. Every one of those atoms was, before that, part of the same hot, dense plasma that filled the universe in its first fraction of a second. And every part of that plasma traces back, without exception, to a point smaller than a proton, a point that may itself have emerged from some process, some prior state, that current physics has no reliable way of describing. The chain of connection runs unbroken from the first instant to this one, even where the far end of that chain disappears into genuine uncertainty. 2 journeys were promised at the start of tonight's documentary, and 2 journeys have now been taken. The first carried you backward through 13.8 billion years of real, well-measured cosmic history, from an ordinary night sky to a point smaller than a proton, tracing a path that telescopes and instruments have confirmed, layer by layer, across decades of careful observation. The second carried you past that point entirely, into territory where confirmation gives way to careful, honest speculation. 4 serious ideas standing at the edge of what can currently be known, none of them proven, none of them disproven, all of them still waiting on evidence that may never arrive. It is enough, for tonight, to have traced that chain as far as it can currently be traced. Somewhere out past the edge of what any telescope will ever see, past the boundary where physics itself stops offering confident answers. The true history of everything may still be waiting to be understood. Or it may not be waiting at all. It may simply be unreachable. A closed door rather than a locked one. No key required because no key would ever fit. Either way, the universe visible from here, the one built across 13.8 billion patient years from that first impossibly small, impossibly hot point, is enough to sit with quietly as the night continues on. Somewhere above, whether or not the sky happens to be visible right now, that same ancient light is still arriving. The faint microwave hum of a moment 380,000 years after the beginning, filling every direction equally, indifferent to whether anyone below is awake to receive it, indifferent, too, to whether the question of what came before it is ever finally answered. It has been traveling for nearly 14 billion years to reach this particular moment, this particular quiet room. It will keep arriving, the same way it always has, long after the eyes reading these words have closed for the night, carrying, in its own faint and patient way, the oldest message the universe has ever sent.